Ever wondered how your phone's antenna manages to lock onto signals with such precision? Or why some devices struggle with reception while others thrive? The answer lies in the invisible art of antenna design, a field where nanometer-level adjustments can transform performance. But creating antennas that work across multiple frequencies, fit into shrinking devices, and maintain signal integrity isn't just about trial and error. It's a multidisciplinary challenge rooted in electromagnetism, materials science, and now, machine learning. Let's dive in. Antennas are the unsung heroes of wireless communication, acting as both receivers and transmitters for electromagnetic waves. But designing one that efficiently operates across 2.4 GHz Wi-Fi, 5G wave bands, and everything in between. Traditional methods rely on computationally intensive simulations and iterative manual tuning, a process that can take weeks for a single design. Enter machine learning, a paradigm shift that's rewriting the rules of antenna optimization. Take the 2020 study by Murat Temiz and Vemund Bakan, which focused on double T-shaped monopole antennas, DTMAs. These structures are prized for their compact size and multiband capabilities, but their performance hinges on precise geometric parameters. The researchers trained algorithms to predict how variations in arm lengths, T-junction angles, and substrate materials would affect key metrics like return loss, bandwidth, and radiation efficiency. They tested regression models, essentially mathematical approximations that improve with data, as well as gradient-boosted trees and neural networks, which mimic biological learning processes. By feeding these models thousands of simulated designs, the algorithms learn to identify optimal configurations in seconds, not weeks. The results? Their machine learning framework didn't just accelerate the process, it uncovered designs that outperformed human-engineered solutions. For example, the model identified non-intuitive T-shape ratios that expanded bandwidth by 18%, while reducing signal distortion. Imagine applying this to 5G massive MIMO systems, where hundreds of antennas must coordinate in real time. Or picture smartphones that self-optimize their antenna geometry based on user behavior, environmental interference, or even location. This isn't just efficiency, it's a leap toward adaptive, intelligent communication systems. This study is part of a broader revolution. Researchers are now using neural networks to predict antenna gain patterns, reinforcement learning to dynamically adjust beamforming in real-world conditions, and generative models to explore entirely new antenna topologies. The key insight? Machine learning doesn't replace engineers. It amplifies their ability to tackle problems that were once computationally intractable. So the next time you stream a video or make a call, remember, behind that seamless connection, algorithms are working in real time to optimize signal paths, mitigate interference, and push the boundaries of what's possible. The future of antenna design isn't just faster, it's smarter, more adaptive, and limited only by our imagination.